One of the most important concepts that we've met so far in our study of vector spaces is linear independence. And we define linear independence in terms of the nature of the solutions to a vector equation involving the vectors on one side and the zero vector on the other side of the equation. In other words, linear independence is the question, how many different ways are there to take a linear combination of my set of vectors and produce the zero vector out of it? So linear equations that have a zero vector as the right-hand side are called homogeneous linear equations. So in this video, we want to take a quick look at what is it that makes homogeneous linear equations so special? What properties do homogeneous equations have that other types of linear systems don't necessarily have to have? So let's just take as an example the linear system negative 2x minus 4y equals 0 and negative 3x plus 6y is equal to 0. That's a homogeneous system, again, because the right-hand side is the zero vector. The right-hand side of every equation in my system is equal to 0. So if I want to understand the nature of the solution set to this system, we'll do what we usually do. Package it up as an augmented matrix, find the reduced row echelon form of that augmented matrix, and notice something special already happens in this example. My reduced row echelon form has a row of all zeros in it. And notice that this is going to happen for a homogeneous system always. Not that we're going to get a row of zeros every time, but it's not possible to get anything in that right-hand column other than zeros by doing elementary row operations. And so in particular, something that's never going to happen for a homogeneous system is we're never going to get the 0 equals 1 style contradiction equation coming up in our process, because our right-hand sides are never going to equal 1, no matter what row operations that we do. So a homogeneous linear system is unique in the fact that they are always consistent. There is always a solution. Another way to think about it is that there is always a linear combination of whatever vectors you choose that will produce the zero vector. All I have to do is take the linear combination, all of whose coefficients are equal to 0. 0 times the first vector, plus 0 times the second vector, etc., plus 0 times the last vector. That's always going to give me the zero vector. So I can always make the zero vector out of any bucket of vectors that you give me. And so the homogeneous equation for that list of vectors is always consistent. There's always at least one solution. In this particular example, there happens to be more than one solution, because not only is it consistent, which every homogeneous linear system is, but we also have a free variable, that non-pivot column, minus 2 zeros sitting in there. That's telling me that I have a variable here whose value is not being bound to the values of other things, whose value that I can choose freely, right, as any real number that I like. And since it's the second column, we're going to take that to be the variable y. So if I set y equal to an undetermined parameter a, and then solve for x in terms of that parameter a, and then repackage this solution that I have up here in its vector form instead, what we find out is that the set of solutions to a homogeneous equation, or at least to this homogeneous equation, forms a vector subspace of R2. And the reason we know that is that this set of solutions is explicitly being written as the set of all linear combinations of a particular vector. In this example, that particular vector is 2, 1. So in other words, any vector whose x component is twice its y component will be a solution of this linear system. And so that set of solutions is a subspace. It's a vector subspace of whatever the ambient space is, which here is R2. And we've found a basis for that subspace as well. It's the vector 2, 1. So this process of solving a homogeneous linear system, first of all, we can know right off the bat, if my right-hand sides of my equation are all zeros, I know I'm going to have a consistent system. It's not possible for me to get a no-solution situation. But then as I go through and I solve this system, if I do end up with free variables, if I do end up with infinitely many solutions, in other words, then the process of factoring out those free parameters will actually build for us a basis for a subspace, which is the solution set of this system. And so what this actually does, secretly, this is sort of a 40,000-foot view of what just happened, is that we've shown that every homogeneous linear system corresponds to some subspace. And the reverse is also true. If you give me a subspace of some finite dimensional vector space, I can find some homogeneous linear system of equations whose solution set is that subspace. So we can talk about one of those things by talking about the other. If we want to know something about subspaces, let's learn something about homogeneous linear systems. If I want to learn something about homogeneous linear systems, let's just learn about vector subspaces, which is something that we already did. So, important properties that every homogeneous linear system has. The first is that it's definitely always consistent. Not possible to get a no solution situation. And the second thing to know is that its solution set is always going to be a subspace. And in the process of factoring out the free parameters from that solution set, we will always discover a basis for that subspace that we get for free in the process.